I'm Zhang Xingjian from Prof. Alex Group. Here is the collaboration we work in our group and Prof. Weibo's group. The topic is quantum key distribution over dipole fiber with room temperature telecom-band single sources. So for the demands of QKD has existed for a long time because of its theoretic information security. And a huge class of QKD protocols is called prepare and measure protocols, where one of the user here prepare a particle, or a modulated particle, and send through the quantum channel for the other user to measure. And they have another channel for classical or public communication. So it becomes important that in a QKD source, we need as much singles as possible. So if we take photons as an example, here's an imaginary graph of the time distribution of photons. Sometimes the photons come together, which is called bunching, and sometimes the photon comes separately. So in QKD, what we care a lot is the ratio between the single-photon events and the multi-photon events. We want this ratio to be as high as possible. So, however, different sources have different tendency to emit single photons. For example, a thermal sources like the sun tends to emit multiple photons at once, which means the photons are bunching. So if you have a detected photon and see like how much possibility you have to detect another photon in the nearby time zone, you will have such a plot, which means you have higher possibility to detect another photon around the same time. However, for the lasers, because we know the lasers have very regulated phase. So in other words, the photon number of the lasers is totally random. And the correlation function of the lasers is just a flat curve. However, for another kind of sources, for example, a two-level system with an electron, it is occupied. The electron itself is occupied once a photon is emitted. So the photon tends to come one by one, or say it's anti-bunching. So the G2 curve of such sources is a dip. We use the normalized second order correlation function at zero delay to evaluate the tendency of like how the source tends to emit photons. For reference, a laser have G2 equals 1 usually. So the more close you are to a single photon source, the G2 is more close to 0. And most single photon sources sits between 0.5 to 1 or 0.5 to 0 or 1 to 0. So if you use a laser for QKD works, this is the Poissonian distribution of the laser of the number states. You find like to achieve a very high single photon to multi-photon rate, you need to always attenuate the laser until it fits your channel condition. Or you can improve that by using decoy state method, but you cannot like absolutely solve this problem. However, let's think if you have a very ideal single photon source like this, T2 equals to 0. So it always emits only one photon per pulse. Okay. Yes.
Your axis on the previous are wrong, right?
Yes.
It's at 0 here, right?
Yeah, we should have a 0 here, but
you cut the 0.
Yeah, I just cut the 0. Yeah, because the 0 is not detected by the band ball. So, so you will find this ideal single photon source always only emits one single photon per time. So you don't even have to attenuate it in any chance. However, most of our single photon sources in the real reward is between the ideal case and the total poisoning case. So for comparison, you can see like with the same mean photon number, the Poissonian distribution have less single photons than a sub-Poissonian distribution of its single photon sources. So in the past decades, a lot of very novel materials have been explored as single photon sources and applied in quantity distribution. Here is a chart for some recent pioneer works using single photon sources for QKD. And you can see like most of them works in the wavelength shorter than the telecom-band, which is at least 1280 nanometers. Which means most of them can only propagate in either in free space or dedicated fibers, which is very expensive. And what's more, most of the emitters is in cryogenic condition. Only several. I only saw like 4 or 5 room temperature single photon sources. So room temperature single photon sources didn't really have a chance to be utilized in quantity distribution, especially the deployed fiber quantity distribution. In 2018, Prof. Gau's group, Prof. Weibo's group, have found a defect-based emitter on the gallium nitride sample, and they put this sample onto the patterned sapphire substrate, like these coin structures. Yeah, I found the emitters to have anti-bunching characteristics. The wavelength of these emitters is between 1100 to 1350, which partially overlaps with the telecom-band. So we use a confocal microscope to scan through all the emitters randomly distributed on the sample. This is zoom out scale how basically the sample and the coin structures look like and how the emitters distributed randomly on the structures. So we scanned a lot of these kind of emitters until we find the best one comprehensively, which means it's bright and it has the correct central wavelength, which is very close to 1310 nanometer. And it have not bad G2. It have a relatively narrow emission bandwidth. Everything seems okay. This is the emission spectrum of that emitter we found. The full wave half maximum is around 7 nanometers, which is not narrow compared to like most of your spectrum, I think. Yeah, but like in room temperature sources, it's actually already very narrow. Because room temperature sources, perhaps because these sources usually coupled with phonons, so it's very sensitive to thermal noises. So this bandwidth actually make the coherent length very short. So you can do some funny stuff like this. So we put the photons from this emitter into something similar to a match sender interferometer like this. And by tuning the delay between the 2 arms of the anti-interferometer, we can see like how the visibility of the interference patterns changes or it drops when your phase difference is too big. So you can see after around 50 waves, the visibility have dropped a lot. So our coherent length is pretty small, which made up a lot of difficulties we are going to talk about later. Then we measure the G2 function under different conditions. This one is under continuous pump, and this one is under pulse pump. Both G2s have confirmed like there is single photon anti-bunching. And what I want to stress here is this G2 number is not measured under a very faint power to get a good number. This is using like exactly the same pump power as what we use in the quantity distribution later. So far so good, and we try to simply shoot the single photons through the fibers. The superradiance thing we firstly found here is the lifetime of this emitter locally. It's very, very narrow. It's like about 300 picosecond. Which means it has potential to achieve very high repetition rate because it recovers fast once it emits one photon. And another thing we found is if we shoot this thing over a fiber, because the 1310 nanometer is the zero dispersion wavelength of commercial fibers, so the pulse shape is kept very well, even if it's propagating over a 32-kilometer spool. And we also try to distribute the photons from NTU to here, and also the clock signals as laser processed from NTU to here, and see the lifetime. So the lifetime is still not bad, but we are not sure like how much of the increase is because of the resolution of the clock distribution. However, we encountered some problems when we try to distribute the polarizations. So as we said, the coherent length of this source is pretty small. So we found the polarization state actually becomes slightly mixed after distributing over the fibers, especially the deployed fibers. So we use the tunable laser to scan through different wavelengths and found the polarization trajectory to scatter like an arc or say like a flower, whatever you want. Yeah. So the left case is over 32.5 kilometers spool, but the right case is only over 3.5 kilometer deployed fiber. Polarization entanglement sources actually also found these kind of problems. His polarization scattered from like within 100 nanometers. So he had to filter his source down to about 20 nanometers until the QBER is acceptable. Yeah, this effect is due to the polarization mode dispersion, which is called PMD, and the random environment like stress and temperatures and the jackets on the fiber act different in different parts of the different segments of the fiber. So if you split the fiber into a lot of tiny segments, every tiny segment acts as a small wave plate with different directions of your axis. So a recent paper showed that this effect, the distortion of polarization due to the PMD effect, will be minimized by choosing the basis selection smartly. All the four states are equally scattered to the maximum angle. This is obviously not very clever. So what is better is this case. If someone puts two of his states along the polarization mode dispersion vector, so what we did is actually made this true. So this is the polarization trajectory against wavelengths in the deployed 3.5 kilometer channel. I really like how this fits with the theory, but yeah. Although it still have some imperfects because of the second order PMD and the time variation during the experiments. So in the following experiments, we chose this kind of scheme because if you have very unbalanced QBER, like in this case, this QBER is very small, this QBER is very big, you can actually gain some key rate from the key rate analysis. Yeah, here's the final setup of the polarization encoded BB84. And FPGA board controls the synchronization signal and the pump process. 1064 nanometer pump process come into the sample by the confocal microscope, and the emission is reflected and passed through this dichroic mirror and collect it into the fiber, go through this part, which is key polarization encoder, which is zero order. And then we tune the polarization before entering the quantum channel to minimize the effect of PMD. And after coming out of the channel, everything seems regular, like just another polarization pedals to calibrate the channel PMD, channel polarization transformation and passive basis selection and two polarization beam splitters and SSPT detectors. This is a Huber and the key rate over 7 hours without any actual compensation at the temperature of polarizations. So the stability of the system permits a long enough runtime and therefore a big block size to overcome the finite key effect. Yeah, like shown here. This black curve is the theoretical limitation of given by our devices, the channel loss, and the infinite key assumption. So you can see we are pretty close to to the best case we can get. And also we found like the biggest limitation here is the polarization mode dispersion, which is preventing us to perform longer distribution longer distance QKDs. So we carried out the experiment in another 32.5 spool, which have much lower polarization mode dispersion parameter, and found it still holds very good key rates, even though through the much longer fiber spool. We also carried out a 10B encoded version of quantum key distribution with the same sample. So this is a scheme of the setup. The same confocal microscopes and same FPGA, but different control programs. What is tricky is it is this Saniac asymmetric MZ interferometer. So the input comes through the circulator and is split at the BS. This is a Saniac interferometer. So if you do nothing, it will come out from here. And the total length of this path is this. Yeah. But if you apply a pi phase on this phase modulator, you will find the Saniac interferometer makes the light come back from here. So that your total path will become this, which is longer than that one. So it is tricky, but this thing basically acts as a active basis selection. And this is the phase modulation simply. We found because time-beam protocols is more robust against the PMD, so we can actually make a longer distance of deployed QKD from NTU to here. The deployed fiber length is 30 kilometers between us, and there's about 7 or 8 fiber joints. And in both sides, this is a very general time-beam decoder, which has unbalanced MZ interferometer. So we carried out 2 different protocols with this setup. One of them is just normal BB84, but the other is reference frame independent protocol, which is a little bit fuzzy. If you want to have a quick sketch on what is the reference frame independent protocols, in the free space satellite cases, the circular polarization is always preserved, no matter how the sender is oriented compared to the receiver. However, the linear basis of polarization is always changing, like the XB and YB. And in the time-beam encoding methods, you will find the long short arm basis is always preserved. However, the phase spaces could drift against time. So the RFI protocol gives you an idea that by calculating these two parameters, the users could estimate the amount of information leakage without actively calibrating for the phases. The key rate is still positive, but we didn't get enough key rate to overcome the finity set defect for the RFI key rate also. But I think this result itself is fantastic enough because we really distributed some quantum key in theory, secure key in theory from NTU to here. And here is a comparison between our experiments with different encoding methods. So you can see for time-beam protocol is much more robust against PND. In the 30-kilometer deployed fiber, it only gets like around 7% Q-ber, while our like 3.5 kilometer polarization encoding protocol got around 5% error Q-ber. What's more, the time-beam protocol is more suitable for the RFI protocol. Like no matter in free space or fibers, but we are talking about in commercial fibers. So the polarization states is not compatible here. However, the polarization protocols have less lossy decoders because the time-beam encoder and decoders always have these fiber combiners. Every time you combine these lights with the fiber combiner, you lost 50% of the photons. So in this case, you have two. And what's more, polarization encoding methods don't need any active compensation on the temperature or polarization because we found the polarization to be pretty much stable. However, the time-beam encoders and decoders were very sensitive to the temperature, so that we have to purchase a active temperature stable system for these two NZI interferometers. This is actually also because of our like low coherent length. So if here's a chart comparing to all other pioneer works using the single photon sources for QKD in resetting. I have marked the advantages of every term in green fonts. So you can see only the cryogenic single photon sources was used in deployed fiber, and some of them is using frequency conversion, which gives you only around 50% or 40% quantum efficiency and a lot of noise. And some cryogenic emitter is in the telecom-band and can naturally propagate in the deployed fiber, but all the room temperature sources already published didn't do any deployed fiber experiments. They're only doing like in-lab free space and using the attenuators as at their quantum channels. Yeah, we are holding a not bad key rate compared to other works with calibrated loss. However, I want to point out that our real shortcoming here is our extraction efficiency from the source. Other sources have basically percent of extraction efficiency from the source, but our source only have like 0.4, like you only collect one photon per 40K pound pulses. So it's easily low, but a good news is gallium nitride is a pretty mature material and it's easy to be integrated into photonic crystals, photonic structures or waveguides. The emitter is to improve the collection efficiency of the brightness, perhaps by integrating. And the second thing we can do is to improve the G2, which is actually not very low. I didn't like mark the G2 here, but our G2 is 0.3, while the G2s could go to like 0.0005, something like that. Yeah. Actually, Prof. Weibo already had some efforts by making the external cavities around the emitters and trying to optimize the emission bandwidth and G2. And the third thing, the third potential of this source is because it's room temperature, it doesn't need any bulky cooling down system or frequency conversion system. It's actually very suitable for integrating into the commercial models. Yeah, and here are the references.